Welcome to the next session. So in this session we are going to see about the non-volatile memory devices. So in the previous session we have discussed about more and more about volatile memory. We've seen the how to do the read and write operations of your SRAM and DRAM. So in this session we are going to talk about the non-volatile memory architectures like ROM and PROM and its subclassifications also, right? So all of us knows that this ROM is going to be comes under the category of the non-volatile. So non-volatile in the sense there is no need of any longer power to retain the data which is already stored on your memory element. So that's what we can say. It cannot the data is in order to store the data, in order to retain the data which is already stored, there is no need of any power. It's going to be required for continuously to be there in the memory element for the memory element. But here the thing is that the other way we can say that the data is going to permanently stored on your ROM even there is a power or no power. But the another peculiar thing about the ROM is nothing but the data which you already stored, it cannot be modified or it cannot be erased by the user. I'm just talking about the starting time of the ROM architecture, because nowadays we are using flash. That is erasable, you know. That is a way in which the gradual growth of the non-volatile memory is going to be developed. How come we can able to make use of that non-volatile memory even for erasable? Previously, when at the initial point, it is not erasable. So we can call it as it's going to be a masked ROM. The best examples we can say like the digital watches and calculators and the gaming consoles where we are using some memory architectures. There the data will be already written, how the way in which it has to be get accessed or it has to be get operated, so that it's not possible to change by means of the end users, right? So with this concept we will get into the classification of ROM. So where we can able to see some set of classifications where the first category is nothing but a masked PROM technique. So where the data will be written during the chip fabrication, right? So at the time of fabrication of IC itself, the data is going to be getting stored on your ROM and it is not possible to be changed by the end user. And the second category is nothing but fused ROMs. So here the data will be written in terms of the electrically blowing the fuse. That means when the data is going to be getting written here, let's say for example I am having the fuse between the row and column. So if I want to write some data on the particular space, particular the memory, particular the location where at which I want to store the data, so I can electrically fuse this. That in the sense, once the fuse is done, what is the meaning? The data is written on it, and after that this path will become open like this. This path will be open, become like this, so we can't able to go for the again the writing operation will not be possible, so we can do only once, right? And the next category is nothing but programmable read-only memory, or in short term we used to call it that is a PROM. So here the data is written after the chip fabrication, so we can write it in terms of after the chip fabrication is also possible. So that is the reasons why we are going for the program. That is the reasons why we name it as a programmable read-only memory, actually PROM, and followed by we have erasable PROM, right? In the previous case of PROM, we are writing it, and after that, if it is erasable, no, it is not possible to erasable. But to make it erasable, we are going for erasable PROM. So where we are making use of the UV light traces for the erasing of data what you are stored on the PROM architecture. That is the reasons why we call it as a erasable PROM. On other terms we used to call in short form, that is nothing but EPROM. So and followed by we have developed EEPROM, that is nothing but electrically erasable programmable read-only memory. So that means instead of your UV rays, we can make use of the high electrical signal or the low electrical signals through which we can able to erase the data what is it available on your memory. So that is possible. Then followed by we have flash. So flash is the present modern trend what we are using as one of the non-volatile memory device in our hand. It is very handy and it is possible to be done by means of following the same methodology what it adopted in the EEPROM, but it is going more faster and it is more compactable due to the continuous development on the non-volatile memory architectures, right? So let's see how come the general memory architecture of ROM is going to be getting available. So we can able to see that it having a size of m cross n. Okay, where generally we will talk about the memory architecture, the memory size, or the memory array format, how it is going to be getting available, that is nothing but m cross n, where m is indicating the words and n is indicating the number of bits in a word. Let's say for example, let's assume that I have a word 1, the word 1 if I am going to available like this, okay. So let's say I have one first bit, second bit, third bit, fourth bit, fifth bit, sixth bit, it is going to be getting available, right. Like that I have let's say like that I have 8 words is going to be available like this, 1 2 3 4 5, 1 2 3 4 5 6. So what is the size of this particular memory? I can able to say that m must be m number of words. How many number I have? 8 number of words is going to be available, 8 cross, and n is nothing but the bit size of your word, that's n bits per word we can say. Accordingly here I have word 1, I have 6 bits, so I can say it's going to be 8 cross 6, that will be the memory structure is going to be getting available. I hope you can able to understand now. That's what we say here, m words of n bits each, and that we can able to if you want to make it more practical to put it in forward, we can write in terms of the address input signals, we can say that it in the form of log 2 of m, or we can say that m is equal to 2 power k words, right, 2 power k words. So we can write 2 power k cross n read write memory architectures if you want to make it more convenient. And here the a0 to ak minus 1 is indicating the address lines, and q0 to qn minus 1 is going to be acting as both the input as well as output, because all of us know from the concept of your volatile memory itself, your this is equal to your bit line. You may remember what we studied in the non-volatile. So based on the read or write operation, this qn to qn minus 1 either will be acting as an input or else it is going to be acting as an output. So accordingly, whenever we are going to do the read operation, we can say that this q0 to qn minus 1 is going to be acting as an output. Whenever if you are going to do a write operation, we can say the q0 to qn minus 1 is going to be acting as an input for your memory structure, right. And there is one more element is available on the memory structure, that is nothing but enable. So that is the enable is the line, it will be acting as a word line what we have studied in the SRAM, right. To enable the column we can able to enable it, and here we can able to access the so to enable not column, to enable the row we can able to make this enable device, and then we can able to do the operation, either you want to do the write operation or else if you want to do the read operations, we can able to enable it accordingly. So that is what we can able to see it as a memory architecture, general architecture of your ROM read-only memory architectures, right. Let's see that one of the best example what we can do, that is nothing but 8 cross 4 ROM is going to be get available, right. So you can see that previously we seen that here we seen about the how the memory external view is going to be available. Let me see how come that internal view of the memory is going to be available. So we can say that internal view, previously we seen the external, now we are going to see that internal view. So you may remember that in previous of your external view we written as a 2k cross n, we seen 2k cross n, we can see that in the previous case, right. And you may remember this is nothing but m cross n structure, right, m cross n structures. So how we can able to write it is nothing but 2 cross 3, 2 power 3 cross n, that is nothing but 4 we can write. For 2 power 3 cross 4 we can see that what is the size of the decoder is going to be required. In internal, what is the size of the decoder is going to be required, we can say that this is nothing but k cross m size of decoder is going to be required. So what is k now? K is equal to 3 and m is equal to 8, so we required 3 cross 8 decoder is going to be getting available. That's what we say. So you may understand now, we require k cross m. So we can say that k is equal to 2 power 3. So we can k is equal to 3 and m is equal to 8. So we can write it as 3 cross 8 decoder is going to be getting available, and we can see the right hand side structure accordingly over there. And we can see that word 0, word 1, word 2 all are is going to be getting available over here. And what is the value of your Q0? Q0 is nothing but we already seen that Q0 to Qn minus 1. So where the n is equal to 4, we can say that Q0 to Qn minus 1, that is equal to Q0 to Q3 is going to be possible. That is what we can witness over here, Q0 to Q3, right? And since we have the 8 cross 4, we can say that we can assume that like 0 0 0 0 0 1 0 1 0 0 1 1 and 1 0 0 1 0 1 1 1 0 1 1 1. So we can say that it can be word 0, it can be word 1, word 2, word 3, this will be word 4, word 5, word 6, word 7. On the whole, we have W0 to W7, word 0 to word 7 is going to be getting available. So now we can see that what kind of input I am going to provide. So let's say that decoder sets the value of 0 1 0. So what is the meaning of decoder sets value of 0 1 0? That is nothing but we are going to select the word 2 on the architecture. See that in the word 2 in the architecture, what is it available? In the word 2 we can see that here the points are connected, here the points are connected, here the points is not connected, here also the point is not connected. So wherever the point is connected, we can say that logic 1 is going to be getting assumed. This is logic 1, this is logic 0, this is logic 1, this is logic 0, because there is no any connectivity. So we can, what is the output can be done if we are going to make this, sorry, this is nothing but A0, A1, A2, because we need 3 cross 8 decoder, right? So we are, what is the input we are giving? We are giving 0 1 0. Accordingly we can able to select second word line. So according to the connectivity points over here, so it's become 1, it's become 0, it's become 1, it's become 0. So that the output is going to be 1 0 1 0 from the structure. So that is a way in which we can see the operation of the ROM, how it is can be done from the architecture of 8 cross 4 ROM as an example, right? So followed by we see the masked ROM, because we seen about different types, we have to discuss about each and every category. We are just talking about the masked ROM over here. So this is connection is during the time of fabrications we can set. So once during the time of fabrication all the data is written on it, we can mask it on it, and it is having only low writability because we are writing only once during the time of fabrication. But once we return, what we already discussed, we can able to have the permanent storage inside your device unless there is no power on the device, no issues on that. And typically used for the final design of high volume systems, we can use it like where we can able to have some pre-programmed data has to be required for any kind of applications. We can go for this kind of a masked PROM architecture, right? Followed by we are going to talk about the EEPROM, sorry, not EEPROM, erasable programmable read-only memory. So as we seen at the first slide, here we are going to make use of the UV rays as a medium, as a element which will support for the erasing operations on read-only memory device. So all of us know the structure of MOSFET. Yes, correct. Let me assume that N MOSFET. Okay, if I take N MOSFET, so here I have a source, here I have a drain, and here we may have your SiO2, that means your dielectric medium. On the top of it we may have a VG, your gate voltage is going to be getting available, and this is going to be SiO2 is going to be getting available. So all of us know that this will have a P substrate, right? Correct, yeah. So all of us know that when this N MOSFET will be in the on condition, so when this MOSFET will be on, when there is a VGS is greater than VTH, we can say that your device is going to be in the on condition. Why? Because at the point of VGS greater than VTH, there will be a sufficient amount of charge carriers will be available at the point of channel between the source and drain. We can say that there will be a current flow going to be happen between the charge will be start to flow between the source and drain. So the current flow will be in the opposite direction of the charge. So we can say that there is a current is going to be getting available. That's what we know normally. But in the case over here of the erasable programmable read-only memory, we are not going to make use of the normal structure of the MOSFET. Rather, we can go for a floating MOSFET. So what is a floating MOSFET in the sense? We can see that from the diagram over here, there is no any dielectric medium between the gate and the body or in the channel. So here the dielectric medium is going to be getting removed, it's going to be like in a floated point, or else we can say it's going to be a floating gate is present on the top. So we are just exploring only this point. You can see that this point we are exploring over here. So what will happen? If I'm going to increase the VGS? If I'm going to increase the VGS more to high positive, when you're going to increase the VGS of high positive, because of this positive charge at the VGS, the more number of charge carriers which is present on the channel will start to attract towards the gate. That means a floating gate. So what will happen at the meanwhile, the more number of charge carriers is going to be start to accumulate at the floating point, and there is no any sufficient charge is not present on the channel to have a conductance between the source and drain. So previously it was the charge carriers is present at the channel, there is a current conduction, but now due to the high VGS, all the charge carriers starts to move towards to the floating point. It is available at the floating medium now. So there is no any sufficient charge is not present on the channel. So this we are making that become logic 0 at the MOSFET, right? So now what will happen when I'm going to make it back again, that charge carriers on the floating point, floating gate towards the channel, we are going to pass the high UV rays for the time of 5 to 30 minutes. So what will happen, it will push back all your charge carriers which is present on the floating gate medium to the channel back again. That is recreating the logic 1 at your MOSFET. So that is the way in which your EEPROM is going to be getting working with the UV rays over there. So one thing we should remember here, we are using the floating gate MOSFET over here. So at the point when it is charge carrier is moving away from the channel to the floating gate, that make logic 0. When we are going to pushing back the charge carriers to the channel through the UV rays, that we can take it as a logic 1, right? I hope you can able to understand now. So let me come back to the EEPROM, electrically erasable programmable read-only memory. So here instead of using the UV rays, we are going to make use of the electrical signal. Okay, we are going to make use of the electrical signals typically for the normal high voltage, normally for we can make use of the higher voltage rather than the normal voltage to push it and push out the charge carriers from the devices over there, right? And it is going to be more sufficient and more efficient one method what we can follow when we compare with the EEPROM methodology, right? Right, it's going to be very similar storage performance of EEPROM, and it is having more convenient for us to be more convenient for us to be implement. And as an extension of the EEPROM, electrically erasable PROM, we are going to have the flash. So same floating gate principle we are going to make use of it, but instead of UV rays we are going to make use of the electrical supply over here. And the another one important factor about this flash, it's going to be very fast erasable, because large blocks memory erased at once rather than the one word at a time, so that we can erase it in a very quick manner. And blocks are typically several thousand bytes are large, so the erasing will be more faster when you are going to compare with a single word, right? And writes to single words may be very slower, but we can able to pick entire bulk reading or bulk writing, that will be more faster. So that's why we can say that entire block must be read and word updated, then the entire block has to be written back again. And especially we can make use of this flash with the embedded microcomputers, right? And as well as like a digital camera, like MP3, cell phones, nowadays whatever we are using, everything we are going to make use of this flash device as a memory storage device is in the non-volatile memory category, right? Yeah, that's it. So far in this session we have just gone through with about the ROM structure, EEPROM structure, EEPROM electrically erasable PROM, and as well as the flash structures, right? Thank you so much.